G'day chemistry students. In this video, we're looking at dot points 6.3.7 and 8. In particular, we're looking at buffers and the chemistry involved to make them work. Let's get into it. So when we're looking at a buffer, essentially we have a solution of a weak acid and its conjugate base, or a weak base and its conjugate acid. So for example, I could have a solution of vinegar. Its conjugate base is acetate ions, so I could add some extra acetate ions so that there is vinegar or ethanoic acid and acetate ions present in the solution at the same time. When you set these up correctly, what this combination of acid and conjugate base, or base and conjugate acid, can do is resist pH changes when acids and bases are added. And the way that it does that is that there is acid and base that's there to neutralize any of those contaminants that are coming in, which are trying to completely alter the pH of the solution or the mixture. Something to note is that we always form a buffer with a weak acid or a base, and that's because a lot of the particles that are present aren't actually dissociated at any one time. Because there are a lot of particles that are sitting there as whole molecules, those particles can eventually neutralize something, but when the solution is at rest, essentially that pH is not going to be in any extreme. So it's not like we're adding an acid and making a solution that should be sitting at about 6 actually be at about 2. By having that weak acid and only having a small portion of those particles actually dissociated at any time means that that solution can have a pH at roughly where it already is. So if we have a buffer that has a weak acid HA and its conjugate base present, which would be A-, so for example, again, vinegar and its conjugate base, acetate ion, what we would expect to see is that if we were to add a strong acid, we would be increasing the hydronium ion concentration, and that would cause a left shift according to Le Chatelier's principle. Maybe a concept that you might want to revise if that's going to be a little bit fuzzy, because if you were to have a question where you had to justify what's going on, remember that you would have to refer to the rules about Le Chatelier's principle and all that sort of stuff to be able to give a proper justification of what's going on. Here I'm just talking in very basic and general terms. But an increase in hydronium ion concentration shifts everything to the left. In other words, the acetate ion or whatever conjugate base there was would be consumed and would end up producing more HA molecules and a little bit of excess water, effectively meaning that the pH of the solution would be relatively stable. It wouldn't change all that much. On the flip side, if we add a strong base, what that's going to do is react with the hydronium that's there and decrease the hydronium ion concentration. That's going to lead to a right shift. In other words, some of that HA is going to donate onto water to build up that hydronium ion concentration again. The equation below just helps to highlight what's happening at the beginning of that step. The base would be interacting with the hydronium to form Hb+. If we look at a buffer composed in the opposite way, we start with a weak base and we have its conjugate acid, so B and Hb+. What we can start looking at is what would happen when we add a strong acid or base to that. So if we add a strong base, what we would expect to see is an increase in hydroxide ion concentration, leading to a left shift, consuming all of that extra hydroxide that was produced and ensuring that the pH levels remain stable. If we add a strong acid, what's going to happen is that HA, the acid, is going to donate onto some of the hydroxide that's present in the buffer, forming an anion and water. That's going to decrease the hydroxide concentration. There's going to be a shift to the right to bring that hydroxide ion concentration back up and again maintain the pH at a roughly stable level. Last big concept to talk about for today is this idea of buffer capacity. Essentially, there's going to be a point where the chemicals that are present in the buffer are going to all be consumed. Essentially, a point where maybe too much acid's been added and the buffer is no longer able to keep that pH stable. What we would expect to see is something like this occurring. The weak base gets all consumed and then all of a sudden, bang, the acid starts to take over, its pH, the pH of the system drops significantly, and then you end up with an acidic situation there. This break point where we sort of have that big dip or spike in pH, depending on whether we're adding acid or base, is known as the buffering capacity, the point at which it's not really acting as a buffer anymore. As a general rule, buffers can keep a solution within a pH of 1 as long as the ratio between the acid and base, so either the weak base and its conjugate acid or the acid and its conjugate base, as long as the ratio of them is between 0.1 and 10. In other words, if this is in a 1 to 10 ratio or a 10 to 1 ratio, we're all good. We can keep the pH range within a range of 1. So if the buffer is meant to be keeping the solution at a pH of 5, as long as we have a ratio like this, we can keep the pH between 4 and 6, for example. Generally, we start to consider that a buffer is depleted or consumed once we've exceeded either of those bounds for that ratio. Keep in mind, though, that for certain buffers, we may need a buffering capacity that's a little bit more restricted, that the ratio of the acid and the base is even closer than a ratio of 0.1 or 10. And that may be for certain objects or items in industry which need to have very precise pH conditions. Could also happen in natural conditions as well, where things in the environment are particularly sensitive to pH changes and aren't resilient enough to experience and live through pH changes of, say, 1. So, as I said, this is a general rule, but we may find that buffers may have a more restricted capacity than what's been outlined here. Thank you very much, everyone. Next video, we'll be looking at our final concept, which is just exploring some of the buffers that exist in the natural world. But until then, have a good one.